Hello. Welcome to part 2 on the series on Android app controlling W5100S-Pico 2 board as IoT device. In this video, you will look at how local mode and cloud mode interchange each other, how the program locked the functions of the app when there is no internet, and how the code in Android Studio works. I started with connecting the Android device to the board locally to obtain data locally and toggle the light bulb. The IP address on the top suggests that we are using local mode since the IP address is the local address of the board. Next, I turned off the connection. You can see that there is no data on the gauges, and you should not be able to perform any action on the light bulb. After turning back on the network, it would need to take some time before it is able to check for connection with the board. Right now, the board is not operating, so both pressing the light bulb and updating the SFA30 data to send to Adafruit are blocked. Next, as I am starting up the board in Adafruit mode, it would need to take some time before it can receive data. As you see the gauge meter moves, it represents that the board is now online, and you could use the functions even though you are not in the same network. If you connect back to the local network, after some time, you may be able to use the functions again, as now you are in local mode. As you can see, my image is on while the actual LED is off because I turned off the machine while the LED is on, but as I connect back to the local network, the image updates back to the actual state of the LED. This video will explain thoroughly on the getting data and UDP discovery function, but some syntax for the code is not documented. To facilitate the development of my first Android app, I used ChatGPT as my helper for creating functions using Kotlin. The codes to be amended will be centered around these few files. You can find other changes on other files in my GitHub page. Let's get started. At first, I tried using ChatGPT to create the whole app for me, but since I do not understand the overall workflow of Android Studio, I have decided to follow this guide by Help Robot Education instead. This video showed me how to manage elements in the XML files and provided a template of communication between the microcontroller and our device. After multiple tries and asking ChatGPT for help, this is the finalized version of the activity main XML file. On top of the page, it is a text box that shows the current mode of the program. Next, the light bulb is an ImageButton element which switches between two images created with ChatGPT that are labeled bulb on and bulb off. Also, there are 3 edit box elements that shows the category of the data with its scientific symbols. Lastly, I asked ChatGPT for suggestions on showing these 3 data nicely, and it suggests me to use the Simple Gauge Android library by Gruzzer on GitHub. There is also a text box below for debug messages. With the layout completed, let's move to the manifest file. Under the manifest label, add the 2 user permission labels so that the app can access the internet and also read the current network status of the device. Next, go to the build Gradle file to download external libraries for the program. These are the external libraries that I have used for the program. You can find the remaining libraries in my GitHub page. After completing these setups, we can now move to the main code at MainActivity.kt. In this section, I will talk about the codes for turning the lights on and off, obtaining data every certain time frame, detect network state, and the UDP pinging function for the Android device. Before coding in the predefined onCreate function by Android Studio, we first initialize few variables to be used throughout this activity. Firstly, I bind our activity_main XML as the layout of our page. This notifies the app that we will be using activity_main XML for the layout. Next, I use the Ktor library to set up the client to make requests on the internet, which is suggested by ChatGPT. Lastly, these 2 jobs were used for UDP pinging and obtaining data from either Adafruit or local network. Both jobs runs at their own time frame. Inside the onCreate function, we first set the layout and the elements that will be altered throughout the activity. In addition to binding the 3 gauge meters, we need to use this syntax to assign its max and min value and apply colors throughout different ranges. You can find more about the library by going to the GitHub page by Gruzzer. After that, initialize Boolean flags, our account name, the secret key if it exists in our device already, a mutex lock, and the API endpoints. You can go to my Hackster.io page for more detailed explanation or simply follow the video. We can now write the discovery job function first, which is used for UDP pinging. To run a code continuously every certain time frame, we need to use lifecycle scope along with isActive keyword to run the job. The purpose of Boolean for discovery job is to avoid the getData job to make request before running this code. Before starting to find if connected server is on local network or not, we need to first check the connectivity state of the Android device. With the help from ChatGPT, this is the function for obtaining the current network availability depending of the SDK version. Inside the discovery job, we first check the network availability of the device. If there is no network, we display an offline message on the text box above, set all gauges to 0 and disable the image button. If there is online service, enable the image button again. Here is a short demo of the upon situation. Next, if the Android device has internet, we need to search for the IoT device on local network using UDP. With the help of ChatGPT, the function for Discover IoT device is as follows. This function will initialize a socket that sends a UDP message containing the message Discover IoT and send it across the whole network under port 8888. As in the previous video, if the board received this message, it will return with its own IP address to the socket. So, with the IP address acquired, we can simply return this value back to the main process. Lastly, if the time for receiving data is reached, we return null back to the main process. Returning back to the discovery job, we store the function result in a string and see if there is any value inside this string. If the return string is not null, we then set the IP variable with the function result and display the IP on top of the text box. Afterwards, check for the secret key in our app. If there is no secret key, we call to the getKey endpoint of the board. Here is a short demo when the device gets the key. If the device has already stored the secret key, we will then send a request to the default endpoint if the device first connected to the board or the device changes from cloud mode to local mode. If neither of the situation is fulfilled, then we do nothing and wait for the SFA30 result to keep updating from the other job. If we successfully connected to the default endpoint of the board, a sound will be played on the board and the current LED value will be returned to the device and amend the image on the button accordingly. Here is a demo of the upon situation. Note that this delay between starting up and sending requests to the board might be due to the UDP function of the board is not yet starting while the UDP pinging function on the device has already been started and finished, thus waiting another cycle of both device on UDP connection testing. Lastly, if the IP result is null, then we amend the title depending on whether we receive the key or not, as without the key we cannot use the Adafruit mode. At the end of the discovery job, delay 10 seconds before calling function to again. After completing the discovery job, we can now go to the getData job. The getData job follows the same structure in using lifecycle scope with isActive keyword, but it will be ran every 3 seconds. If the discovery job have not been done, we skip the getData job until it is performed at least once. We can then get the SFA30 data locally if the IP is received from the UDP socket. The lock is used to avoid calling other function that uses the same lock that produces error. If the IP is null, then there is a few things we need to check before proceeding to obtain data from Adafruit. We first check if we have the key or not. If we do not have key, we do not proceed to get anything from Adafruit. Then suppose if we have the key, we will need to also check whether the board is now in cloud mode or not by checking the online feed. On the online feed, I only allowed the board to send 1 as online and 0 as offline, so other values except from the value 1 will be treated as server offline. If the server is offline, I just set every value in the gauge to 0. Here is a short demo when the Adafruit mode is offline. Notice that pressing the light bulb will also not work as the server is not online, which we'll implement later. After obtaining the online status of the board, we can retrieve the SFA30 data from Adafruit. To allow the gauge to update the values at the same time, I need to use async library to wait all the response together before setting the values. With the help of ChatGPT, this is how I coded the async and await functions for the values and update the UI at the same time. The run catching function is a simpler way to catch all exceptions in the same way and return a default value for any exceptions. Here is a short demo for updating the app layout with Adafruit. Both automated functions are completed. Now, let's move on to the ImageButton function. Firstly, I avoid users to make multiple calls on the onClick listener by checking the enabled state of the button and exiting the function if the value is false. After that, we can code the actual function after clicking the button. We first make sure our button is set to false first before any action, and we then check if we retrieve the board's IP address or not. We now call to the light endpoint on the board and change the button state boolean on every instance of button press, which helps us change the image on the button. This lock is to ensure the code for getting SFA30 data is either completed or not called before calling the request to the board. In Adafruit mode, we use the same logic as getting SFA30 data, where we check for the key and online status of Adafruit before proceeding to change the light feed. Then, if the board is in cloud mode, we send a payload containing the opposite of the current button state in the form of integer, and if the request is success, we then change the button state. Lastly, we enable the button again, and according to the button state, we change the image on the button. This completes the MainActivity.kt of the app. We will now move to the splash screen of the app. Both the image and the code are generated by ChatGPT, and here is the code for it. Initially, this splash screen will handle some request before accessing the main activity, but it was then removed afterwards, leaving the line finish to destroy this splash screen activity. In the Android manifest XML file, we need to change the activity to show our splash screen first. To do it, simply create a new activity with the SplashActivity class and move the intent filter section from the main activity to the SplashActivity. Lastly, create the layout for the splash screen by setting the activity SplashXML. Create a frame layout and use the image view element and reference the source to the logo inside drawable file. This completes the app for controlling the microcontroller board. Thanks for watching. This project is a new challenge for me, and it guided me to learn more not only about creating an Android app, but also the possible functionalities of the W5100S-EVB-Pico 2 board, such as hosting a UDP socket and a HTTP server. I hope with this video, it also inspires you to create your own version with different functionalities on the board. You can find related links down in the description below. If you enjoyed this video, please like and subscribe to my channel for similar content. See you in the next video.